Our next speaker, we have the pleasure to welcome Professor Davi Maximo from University of Pennsylvania, and he's going to talk about on Morse index estimates for minimal surfaces.
Thank you, Claudio, very much for the introduction and the organizers for the invitation. It's a pleasure to be here. So another minimal surface talk. I'm lucky that Joaquin spoke at length at some points about the theory. I will also focus in R3. But I will take a slightly different point of view in the sense that I will focus on the Morse index. Okay, so let's see. So I just have a few slides on the basic introduction. So as you know, this is a very basic object in geometry, right? In the sense that it's a question that you really want to know about which are the surfaces that minimize area. So I just added here a little bit of history on the Plateau problem, which asks for the existence of surface that has least area spanning a certain curve as a boundary. Now, Plateau, he was a Belgian physicist, and he was experimenting with subfields when he introduced this question. So right off the bat, you see that this theory has a big connection with applied mathematics already, right? And in fact, this problem, I really like to point out the Plateau problem in my minimal surface theory talks, because it's a problem that it's easy to state. It's central, and the attempts to solve the Plateau problem, they have developed a lot of good mathematical theory. So I would like to point out at least the work of Douglas and Rado, where they solved this for mappings of the unit disk. And also this great development that happened in the 60s, which led to the introduction of geometric measure theory. And there you have the names of Di Giorgi, Federer, Fleming, Bombieri. And it's a still ongoing problem and in some sense it's a problem that can never be solved if you think about it, because you can just keep asking for different competitors, right? And I think I also, I like to start here. But for my talk, like Joaquin, I will focus on not area minimizing surface, but minimal surface. So let me explain this difference. So if you wonder how a surface that minimizes area must look like, you might try to write an equation for it if you have a knack for analysis of algebra. So if I write it as a graph and some coordinates, so to be minimal means that the function has to solve this. So it's a PDE, very special one. And you can see that this is equivalent to the mean curvature vanishing, right? But also there is another equivalence, which is the Gauss map of sigma is anti-holomorphic. So these two conditions are equivalent, and in some sense, this is for minimal surface in R3. And this expressed, in my view, sort of two approaches to this theory. So one is more variational. So as you see later, this is the term that appears when you try to do the first variation and second variation of area. But this one, it really shows a big connection that the theory in R3 has with complex analysis. Okay? So I'll start with say a little bit about this approach, and then we go back to the variational theory. Okay? So, and for me, so let's see. So for the first slide, so I'm going to assume that sigma, it's two-sided, so it's just a name for orientable in R3, and embedded. Let's see. And also, in the minimal for us will basically just mean that the mean curvature is 0. So not area minimizing, okay? So, yes, any questions? Okay. Okay, so let's look at some examples. So there's a lot of examples in Joaquin's talk, so let me just go quickly through those. So the catenoid. Oh, and by the way, so I forgot to mention. So one of these things you can see from this is that if the boundary of sigma is empty, so in other words, the plateau problem gives me a lot of minimal surfaces with boundary. If I just pick a boundary that satisfies the condition for the plateau theorem, I can find a minimal surface there. But you can ask yourself, what about minimal surfaces without boundaries? So, well, this will tell you that you cannot have closed surfaces in R3. So if there is no boundary, then it have to be complete non-compact, like in Joaquin's talk. Okay? So this will be, so we'll be looking at those. So let me show you some examples of such surfaces. So the first one, obviously the flat tube plane. I don't think Joaquin mentioned that one. You know, the catenoid, the helicoid. So here's a little picture of the helicoid as almost showing up as a solution of the plateau problem. And then in the 19th century, there are many, many examples found using this approach of complex analysis, the Weiss's representation. Okay, so here are some. So the Shirk surface. So this surface, it's a very interesting surface. If you look from a very far away, it looks like two planes intersecting. But then when you go closer and closer, you see this handle. So this keeps going. So it's periodic. It has infinite genus. So it's an important surface for this desingularization techniques. And this is the Schwarz surface. Again, here it has boundary, but you can reflect this way, reflect that way, reflect. Keep reflecting, you get yourself a triply periodic minimal surface in R3 with infinite topology. Okay? And in some sense, all these examples of the 19th century, they were periodic somehow. So they all have infinite topology. You know. And actually, it was only until 1982 where there was an example found with finite total curve and finite topology. So the Costa surface, which, like Joaquin mentioned, was found here in Brazil. And Hoffman Meeks, they were able to show, Costa wrote the equation for this surface and showed that it was complete. And Hoffman and Meeks proved that it was embedded, so it's really the first embedded example. And then they were also able to construct actually with any genus. So like Joaquin mentioned, this is a torus with 3 punctures. But you could also do it with a genus G and 3 ends. Okay. A couple more recent examples, so the Weber-Wolf and the genus 1 helicoid that Joaquin mentioned, and all the other examples in his talk. So as you see, this approach, you know, has been very fruitful. Try to use this connection with complex analysis to show examples. And more recently, there's been a lot of interest in proving uniqueness questions, like also was mentioned in Joaquin's talk. So you want to prove that certain surfaces with a certain topology, simple enough at least, are unique. But even if you can't show uniqueness, could at least show that the moduli space has some properties. Okay, so this is a very you know, rich topic. But I'll leave it at that and turn to the variational theory for now. Okay. So what I call variational theory? So basically, if I take a surface in R3 and I take a vector field to perturb the surface, I can calculate the first variational area, and this is the expression that I get. The first, I wrote here in the terms, even the boundary term, but if in our case, since we are assuming that sigma has no boundary, so you can just forget about this term, okay? So to be minimal basically means you're just a critical point for the area functional, okay? And so the next step in the variational theory is then to calculate the second variational area. So we basically take a deformation that looks like a function times the normal direction, Turns out that is enough to vary only on the normal direction. The other directions are tangential, they don't change the area. So, and this is the expression we get. So here, this gradient here is the intrinsic gradient. And A is the second fundamental form. So you can do one of my favorite things, which is integrate by parts. And you get that the second variation has this form, as you know, also in Joaquin's talk. So this L is, this operator turns out to be a very nice elliptic operator. So you can talk about the spectrum of L, and that's the number we call the Morse index. Okay? So in other words, like you would do for a function if you were looking at critical points of function, one of the things we learn in calculus, so if a critical point is not really a minimizer, then you can try to understand at least up to second order how many directions you can, it fails to be a minimizer, right? So, okay. So let me motivate you why it's interesting to look at this. So, like I said, this is basically measuring up to second order the fact that sigma is minimizer. But it's actually a very natural property. So from the point of view of geometric measure theory and applications to geometry. So if you think about it, even for geodesics, which are the one-dimensional version of this, right? There's a lot of applications we learn in Riemann geometry. If you know that a certain geodesic has a certain number of critical points and so forth, so if you know the index, so calculations involve index of geodesics, they turn out to be fruitful. So this is from one of the motivations to look at this. But the other motivation comes from geometric measure theory, so which is the current setup to do variational theory of minimal surfaces. So in that theory, you try, I think we'll see a lot of that at Tristan's talk in the following days, but you try to construct this unstable, you try to construct these surfaces that are not minimizers, right? You use this procedure which is called the min-max procedure. So it's kind of like a mountain pass procedure. And so you have to work in a space that has good compactness properties, so you have to leave the world of smooth surfaces. So you work in sort of space of generalized surfaces. You could pick a favorite, it could be currents or varifolds or flat chains. Well, depends on what you're interested in. But the point is that to get that compactness, you have to work with very weak convergence. And so it's kind of hopeless to to try to control the topology of the surface we will produce. So I'm going to do a min-max here, so will construct a torus. So because since even if you start with tori, the thing could pinch off, and then in the end you could get a sphere. So there's this problem of the convergence being very weak and making it hard to control the topology. But one thing you can hope to control is the Morse index. So if the number of parameters that you introduce in this min-max procedure turn out to be related to the Morse index of the surface that you will end up with. So let me show you some of the examples. So for example, of the known surfaces where so this is the catenoid. So it turns out the catenoid has Morse index 1. So to prove that the catenoid, it's not a minimizer, it's easy. You just have to squeeze the neck. You just show one direction where you can decrease the area. But actually, to show that there are no more than one direction, you need an argument. Okay? And here's the Costa surface, which is the next embeddable case. So turns out that this guy has index 5. So that's already a bit mysterious. Why are 5 directions there? So you see, I can imagine squeezing this neck, squeezing that neck, and then the neck here below, but I, at least visually, cannot see the other 2 directions. Okay? So maybe the necks interact, and it is actually, this is a hard paper by Nayatani to show that this has index 5. Okay? What about the helicoid? Well, could you guys, anyone guess? A non-expert? has infinite index. The reason is it's periodic. So once you find a certain direction that decreases the area, you can just go up in the helicoid, and then you find another one, and then you find another one. So you can find an infinite dimensional space of directions that decrease the area of the helicoid. So you get something with so I like this example in the sense that shows you why to assume finite index, it's much stronger from the analysis point of view and the geometric point of view than assume finite topology, because you see the helicoid has, well, what you call trivial topology. It's just a plane, right? But it turns out that the geometric picture of this is very complicated, and it's a major obstacle in proving all these results that Joaquin showed, is to understand like how because the limits of you can have a line of singularities, right? Whereas for the catenoid, if you see the catenoid, you can take the catenoid and you can rescale it, and it's still going to be a minimal surface of index 1, okay? So I can take a sequence of rescaling of the catenoid that converge to the plane, right? And it's going to have just a point singularity. So you see, so no lines of singularities, just a point of singularity. So, and as Joaquin mentioned, the sort of connection between index and topology or total curvature, right, was found by this work of Fischer-Kolbrit, where she proved that something has finite index if and only if it has finite total curvature. And the idea somehow is that if you have finite index, then there must be a compact set where outside you cannot find directions that decrease the area anymore. So they have to stop. So in other words, your surface must be what we call stable, so which is just a synonym for index 0. And so in other words, a surface with finite index, the ends, they're very nice. They're stable ends, So from that you can show that the curvature has to decay and then be integrable. Okay? But okay. So one of the things that I'm interested in then is this relation between index and topology. So this question, I started thinking about it because of this min-max procedure. So we do a min-max, you produce a surface of a certain index, but then what's the topology like? You want to say that it's limited somehow, right? And the case of surfaces in R3 already has a very beautiful history. So I thought, well, it's a good model to understand this relation, because you see, these min-max procedures, they actually work well in general manifolds. So you can actually expect to have parallel questions to what I'm talking about in those general settings. But somehow R3 seems to be a good starting point. And it turns out that the two are related by the Gauss map, right? So this is already hinted at in Joaquin's talk. So let me show you how. So first, to detect the topology from the Gauss map, it's somewhat easy due to this theorem of Jorge Mix. So you basically just look at the degree of the Gauss map, and then you can find the genus and the number of ends from it. Okay? But I'm going to show you why the index can also be read from the Gauss map. It's all there, okay? And it uses this miracle in R3, so which is that the norm of the second fundamental form is equal to minus 2 times the Gauss curvature. So this is a miracle that makes a minimal surface theory in R3 very, very, very special and makes you able to go very, very far. You go to R4, that's not there anymore. So this connection with complex analysis. Okay? So let me show you how the index is connected and why is it elusive. So this observation comes from this fact that if sigma is minimal, then the Gauss map is anti-holomorphic. So this word here, anti-holomorphic, just means that it's a holomorphic map, but it changes the orientation. Okay? So here's a map from the canoid. So it's conformal. So let me use the chalk board here real quick. So what is the idea? So that I have n, like, can you guys in the back see this? It's big enough? Yes? Okay. So basically, this map allows me to put in sigma 2 metrics. So one metric, let me call it H1. The only pain you see in doing this, this sort of like a minimal surface theory in R3 is that you have to use G for genus, and then you cannot use it for the metric anymore. So let me call it H1, the metric just coming from the R3 metric reduced to sigma, the induced metric. And I'm also going to take the other metric, H2, which is just the pullback by n of the standard metric here. S2, okay? So it turns out that if sigma is minimal, then these two metrics are conformal, okay? And this metric here, you see it's a very nice metric in the sense that, well, it has constant curvature. This is the round metric in S2, okay? So even if I go to find, if I look at the second variation, which is equal to this, so here I use the metric H1, but then I can rewrite this. So it turns out that in dimensions 2, the energy, in other words, the gradient squared times the volume, this is a conformal invariant. So I can just write this in the other metric like that. Okay? And then this guy here, a squared, this is just 2 times k. But k turns out to be the degree of this map. So k times d vol h1, it's just the Jacobian of this map. So in other words, I end up with plus 2 phi squared times the vol of h2. So in other words, to find the index of my minimal surface, instead of working with this quadratic form, I could just work with this one, which I got from the Gauss map, okay? And this is a better metric from the point of view that it has constant curvature, okay? So, but there was a not so small issue here, which is that H2 is not really a metric. So what is the issue? So there are branch points for the Gauss map. So in other words, there are points where this guy, the derivative of this map vanishes, so I cannot pull back. And they just happen to be lying around my surface. I don't know what they are a priori, but by just looking at the surface, it's kind of hard to say, oh, here's a branch point, here's another one. So in other words, H2 has a metric of constant curvature, but it has these singularities. You can try to see like locally how they look like, if they're conical or something, but it turns out that it's very hard to somehow use that metric to find an index bound. Okay? I mean, you could say, well, it's an L2 theory, so points, they shouldn't really matter, the singularities, but it turns out that they do. But anyway, I'm at least, this is at least an argument saying that there is some relation, right? So it's all in the Gauss map. Okay. Okay, so recently we were able to show this estimate. So if you have a surface in R3 of genus G and Rn's, then the index has to be at least this much. Okay? So this was the first bound to capture the number of ends. And the reason that it's It's subtle. It's because, like I was saying, a surface of finite index has to be stable outside the compact set. So the ends are stable. You don't really get variations by just deforming the ends, right? Somehow you have to, just a local argument, oh, I have this end here, I'm going to push it down a little bit. Doesn't work. It's stable there. So this was the first lower bound. Upper bounds had been known for a while, so there's this work of Tisk, that was also in Joaquin's talk. And the idea of the upper bounds is that once you know the conformal type of a surface, it's somewhat controlled, right? So it's genus G and Rn, so you control the whole conformal structure. So somehow you have a controlled situation, so you can control the index from above if you know both G and R, right? So that's sort of morally how you get an upper bound. So it's slightly easier, I would say. But if you combine this with the Shorty mix formula, then we arrive at this theorem saying that, so it's a quantitative version of Fischer-Kolber's result, right? And again, this assumes that sigma is embedded, because otherwise the George mix formula changes slightly, okay? So this follows just from Tisk, like as mentioned in Joaquin's talk, and our bound gives this lower control. But the other feature of that bound is that it allows us to push a little bit the classification of minimal surface with a low index. So it turns out that as you could hope to classify minimal surface with small topology, say you have a minimal surface that has a plane, or it has genus 1 and 3 ends, and you want to know what it is. You could also ask yourself, what are the minimal surfaces with small index have to be like? So it's been known for a while that the only stable one is the flat plane. So basically, being a minimizer up to second order, it actually makes you be the minimizer in this case, okay? For index 1, it has to be a multiple of the catenoid. A multiple, I mean, you could take your catenoid and just scale by how much you want. It's still going to be an index 1 minimal surface. It's a work by Lopes and Ross. So using that bar, we're able to show that there is no minimal surface with index 2, so there is a gap. And this is somewhat expected. This is observed in the sphere. And it has to do with the fact that R3, or even this S3, all these spaces that have lots of isometries, those isometries, they create nullity for your surface. So in other words, if I had the manifold and somehow I hammered it a lot, such that there were no Jacob isometries. So one way of saying is that if the metric was bumpy, right? There's a precise way of saying that. Then you know that if the minimal surface exists, then it can have no nullity. And it turns out that the hope is that the min-max theory will say there's going to be a minimal surface of index 1, of index 2, of index 3, of index 4, of index 5. Every integer you can find one. But once you have isometries, one thing that can happen is that some of those surfaces with index, the eigenvalue could go to 0 and become a nullity. This is what happens with the sphere. So the sphere, you have the equator has index 1, the Clifford torus has index 5. As soon as you break those symmetries of the sphere, so you perturb the metric, you get a sphere of index 1, a sphere of index 2, a sphere of index 3, a sphere of index 4. And then something of index 5 and so on. So that's more or less the reason why gaps are sort of not surprising. They're expected in an ambient like R3. And the question is, the only other known example is the cost of surface, which is 5. So one wonders what happens, with index 3 and 4. So recently we were able to show that if a minimal surface of index 3 exists, then the only possibility is it has to be one surface in the deformation of the Costa minimal surface. So the Costa-Hoffman-Meeks deformation family. So what is the idea there? That the point is that this is a one-parameter family of surfaces. So let me go back to the photo of the picture of. So here it is, right? So you have the surface. There is a smooth one-parameter family that basically takes this end here, which is asymptotic to a plane, and you start deforming it up. So the surface is still going to have three ends, two catenoidal going up and one catenoidal going down, and it's a one-parameter family of surfaces. But you see, we know that the first one has index 5. And that ought to be the case for the very first few ones. But as you keep moving the parameter, it could be that the index drops. So you could lose one direction, escapes to infinity somehow, or it could increase. So it's not obvious that it should be the same. And I think it's actually a very interesting question to figure that out. I should say that you could wonder what happens if you keep pushing this parameter to the infinity. Could you find something of index 3? Well, if you push that to infinity, the picture that you get, it's something like this. So if when I start pushing this end up, this neck and this neck right here and this neck right here, they start to pull apart. Okay, they keep pulling apart. So let me rescale this deformation so that they stay at distant 1. When I do that, I multiply my surface by some factor that it's bringing the ends down. Okay? So the picture is going to look like this. So you're going to have some end. And then it's a horrible picture, I know, but but the point is that these ends, because I'm keeping these two necks at distant 1, let's say, the end starts to come down, and in the limit, this converges to a plane with a puncture here, a puncture here, a puncture here. So you think that in the limit, this guy has index 3, because the ends, they look like isolated. I got one end here, one end there, one end here. So maybe the index concentrates at these 3 points as the parameter goes, to infinity. So it's a simple question to know whether, in a deformation family, if the index stays the same or not. Okay? Oops. Now, to mention how we were able to improve from our previous bound, I want to change my assumption slightly, and I'm going to start working with Morse surfaces. So I'm going to forget that the surfaces are embedded for now. So just a two-sided minimal surface in R3. And the reason that one is interested in that is because somehow all the techniques they work for Morse surfaces. You see, they only use the fact that a squared is equal to minus 2k. So it makes the problem intrinsic somehow, right? And another motivation, so there is this focal conjecture that asked whether you can bound in the case of a Morse minimal surface, you could bound the index from below again by the total curvature. Okay? So it turns out that our bound from a few years ago is still true for a Morse minimal surface. Like I said, the techniques, they all seem to only use the surface is immersed. But it doesn't give this conjecture. And the reason is that there is some geometric information missing this bound, the multiplicity of the ends, namely. So when you go to the immersed world, you could have ends of multiplicity. So here is the n per surface, so which is just a sphere with a puncture of multiplicity 3. This guy has index 1. But you see, the end, the way that you go to infinity in this surface, it goes 3 times, right, to infinity. So, and that ought to matter in the calculation of this integral of k scalar. Okay? So, so this year we were able to show this, that if you have a minimal surface with genus G and R ends, and and say that the ends have multiplicity d1, d2, up to dr, then the index has to be bounded by this. Okay? So, and if you put this together with the Jorge-Mix formula for the general one that includes the multiplicity of the ends, then this index estimate turns out to prove that conjecture for two-sided surfaces. So this is a two-sided. Okay, so I'm still assuming that. Now, and how about that result for Costa? So in actually trying to prove this, we realized that we could do a little better than the previous bound. So this is how it works. So you see, if the surface is embedded, then these ends, they all have multiplicity 1. So if you put here dj equal 1, here you will get 4r. Right? So this is better than what we had before. So before, we had 2r. And this extra information allows us to say when we plug in 3 here, we calculate this out, and we'll see that G plus R has to be limited, and then we go through all the list of known minimal surfaces with small topology, and it says that something of index 3 can only have genus 1 and 3 ends. And then we say, we use the classification of Costa that, so it has to be one of the guys in the family. So we are working on proving that, so we have an argument to say that all those guys in the deformation has index at least 4, but we're still checking each other computation. So if my talk was on Friday, maybe I could announce that. but yeah, so we'll see. So, but this is it's a different argument that uses the symmetries of Costa. But anyway, okay. So let me say something also about one-sided minimal surfaces. So it turns out that, and this in R3 is kind of hard to see this, but in general, you could produce a minimal surface which is only one-sided. So for example, in RP3, the RP2 is actually area minimizing. So it's interesting to understand that case as well. Now, how do you define the Morse index there if you don't have a Gauss map? At least, not obviously so, right? So one way to do that is you can go to the two-sheeted double cover, right? So sigma hat. And then sigma hat is going to be a two-sided immersed minimal surface, right? And so you can look at the second variation of that guy, but obviously you're not interested in all variations of sigma hat because not all of them will descend. You have to look for ones that are anti-invariant under the Deck transformation. Okay? So the index of a one-sided minimal surface can be defined as you go to the double cover immersion, you look at the spectrum of the operator, but you restrict it only to functions which are anti-invariant. Okay? So we can somehow apply the method for the immersed surfaces that we showed to that particular case, and then we get an estimate like this. So basically you see the main difference that we lose a factor of 2. Okay? And one of the applications of this formula is to this conjecture of Choi, that in R3 there is no one-sided minimal surface with index 1. Okay? So I should say the two-sided case has been known for a long time that two-sided and stable implies you're flat. And around 10 years ago, Antonio Ross showed that if you are one-sided and stable in this sense, so that's weaker than just being stable. So it's not obvious that shouldn't exist or what it is. So Antonio proved that doesn't exist. So there's no one-sided stable minimal surface in R3. And we show that there is also no index 1. There is an example of index 2, I believe, but there is also no example of index 1. Okay? So let me just say a few words then about how we get these estimates and what is at play here and why these numbers, why we have this sort of, strange looking fractions and so on. Okay? Okay, so, and I promise it will be just a slide. Okay, so the proof uses harmonic form. So you have, in this variational theory, one way to look at it is that you want to prove these estimates, you have to cook up some test functions, right, to plug in the second variation. Now, when you're working with stable minimal surface, anything, you can plug in anything. If the surface is stable, it means that the quadratic form is going to be greater or equal than 0, no matter what function you put in there. But the second you have index, for example, you have index 1, right? So you only get a sign for the quadratic form. Q is only going to be greater or equal than 0 for functions that are orthogonal to this first eigenfunction. And you don't know what the first eigenfunction looks like. So how you can cook up, a test function. So if you don't know, it has to be orthogonal to something that you don't know. So for index 1, there is this, in 3 dimensions, there is this trick by Hirsch that works in general, but it's widely open in higher dimensions and more generally, for more general manifolds, because you really don't know what the eigenfunctions look like, so how can you come up with test functions, right? But, so in our case, we take harmonic 1 forms in sigma, and we use this formula lemma of Antonio Ross. So Ross showed that if I take a non-flat minimum surface in R3 in a harmonic form, then if I take the product of the harmonic form with this one form here, dxk, which is also harmonic, so this guy is just the coordinates, okay? It satisfies the expression, okay? So you see here, minus 2k, this is a squared. So this is almost what you get in the inequality, in the stability inequality, right? And then on this side, you get this term, gradient of the form, dot of h, and then this is the normal vector field. So for every form, you have 3 equations like that. K equal 1, K equal 2, K equal 3. And then if somehow you can make this right-hand side vanish, then he can tell you what the form has to be. It can only be one of these forms where this is the Hodge star, okay, of the dx1, dx2, dx3. So it's like a Bochner type formula. Now, the point is this. So we want to take harmonic forms, take those inner products with the differential of the coordinates, and somehow use these functions as test functions. So that's the idea. So Ross, before our work, he proved in this paper from 2006 that if you take harmonic 1 forms in L2, if you work with harmonic forms in L2, then we can prove that the index is greater or equal than 2g over 3. Okay? So how does he do that? He basically say, well, if the index is smaller than this, it means that the dimension of harmonic forms in L2 is 2 times the genus. Because if a harmonic form is in L2, then the end is a removable singularity. It has a limit, right? So you have 2G harmonic forms, okay? So you don't see the ends if you are just L2. Your surface, your minimal surface has genus G and R ends, so it's conformal to a Riemann surface of genus G and R punctures. But these L2 harmonic forms, they extend across the punctures. So you don't see the punctures, just the G, right? So you take those forms, and if you have too many of them, I can find one harmonic form that all these text functions for dx1, dx2, dx3 are orthogonal to the index. So I can plug in these guys into the stability inequality, and then I can work from there. Okay, so that's sort of the approach of Ross. But our idea somehow is to see, okay, if I take a minimal surface of genus G and Rn, there are lots of harmonic forms, right? Like infinitely many, right? But the point is that, for example, for our first work, we realized that there are some harmonic forms. So if I allow the harmonic form to have a pole like dz over z at the punctures, that's borderline L2. So it's borderline for the Ross proof. So we were able to show that you can actually work with those forms. Okay? Now, for this new result, we actually realized that, especially if the n has multiplicity. So if the n has a multiplicity, then at that puncture, you can actually put these dz, z squared, z cubed, you can go up until you see the multiplicity. Okay? Now the key technical thing is that, we are only allowed to plug in the stability inequality things that are compactly supported. Right? So Q of phi, where phi is a compactly supported function. So if I take this omega dxk, where this guy here omega is not in L2, I'm not gonna be able to plug that in the stability inequality, right? So you have to somehow find a way around that. But we're able to do so, and I'll leave the rest of the details to the paper. But I want to finish by saying that this technique of using harmonic forms, it's fruitful not only in our case in R3. You can also do it for the sphere. So there's a paper by Savo from 2010 where he can show some index bounds for minimal surface of the round sphere. But you can also do it on some other manifolds like products of spheres. This is in the paper of Ambrosio, not Luigi Ambrosio, Lucas Ambrosio, Carlotto, and Sharp. And recently, there is a paper by Radetzky and Mendes and Radetzky, where they do this in a very general case of compact symmetric one spaces, I believe. And so you get expression for the index plus the nullity. Somehow the eigenvalue has to be. Okay? So let me finish with that. Thank you for your attention.
Any questions or remarks, comments?
That's a good question. I think you can do something. There's maybe something done in the free boundary case. I think Ross has something in the free boundary case. So Jose asked if this follows through for the CMC case. And I think if with the right adaptation, yes. So I believe there is even a paper by Ross. I'm trying to think. I think he was trying to prove some isoperimetric inequalities when he started looking at this. So he was actually interested in the CMC case too. I just can't remember exactly which paper he does something about that.
Any other questions? So let's thank the speaker again.